Hello and welcome to the second part of the discussion on the chain rule in this mini-series on calculus at the higher level. So hopefully you're coming to this video just having watched the one prior where we introduced the chain rule of differentiation and gave a derivation, a schematic derivation based on the fundamental results of calculus. That may have seemed a little bit abstract, so now here I want to give a number of examples to show you how this works. So just to set things up, we're looking at composite functions. So let's think of having a function h of x, which is a composite function f of g of x. And what we showed in the previous tutorial was the chain rule, which is that the derivative of the composite function is given by the derivative of the outer function with respect to the inner function, and then multiplied by the derivative of the inner function with respect to the independent variable x, and that is the chain rule. So let's do a simple example first. I just want to show you an example where we can work it out by hand first, the derivative, and then we'll see how much faster and more convenient it is doing this by the chain rule. So let's just have an example. H of x equals a simple function 2x plus 3 all cubed. All right. Now, one way to differentiate this is just to expand this out. Now, I'm going to do this quickly, but you can check this if you like just by multiplying out these three brackets step by step. But if we were to do that, we would get 8x cubed plus be 4x squared times 3, so that would be 36x squared plus, and then it would be 2 times 3 times 3, and then multiplied by 3 again, which is 54x plus 3 cubed is 27. To do that, I'm using something called the binomial theorem, which you would meet at advanced higher. But anyway, that's not relevant to today. Now I can just differentiate this straight away, term by term. So differentiating x cubed, I get 3x squared, and 3 8s are 24. Differentiating x squared, I get 2x, so I have 72x. Differentiating x, I get 1, so I just have 54, and of course differentiating a constant, I get 0. So this is the derivative of that composite function. It's quite messy. We can factorize this. We have a common factor of 6. So I have 4x squared plus 12x plus 9. And then, miraculously, we notice that this itself can be factorized. And it is, in fact, 2x plus 3 all squared, because I get 4x squared plus 12x plus 9. So the derivative is this very neat result, 6 times 2x plus 3 all squared, given this original function. Now I think, even working this out by hand explicitly, you would think, well, hang on, there must be a simpler way to get from here to here than to multiply it all out, differentiate term by term, and then factorize it. And indeed, the chain rule, in a sense, is anticipating that there is a much more straightforward way of doing this. So the much more straightforward way is to identify the composite function. Well, we have an inner function g of x, which is 2x plus 3. And then we have an outer function f of g, which is just g cubed. And these two functions are very straightforward to differentiate. We have that dg by dx is equal to 2, and we have that df by dg is equal to 3 times g squared. And so therefore, putting these two things together in the chain rule, we have that dh by dx is df by dg, which is 3g squared, multiplied by dg by dx, which is just 2. And so I have 6 times g squared, and g, remember, is just 2x plus 3. And so you see that the chain rule gives us a much more straightforward way to do this differentiation. Now the chain rule, though, is not just a matter of convenience, because we can easily think of functions where we will have, for example, a non-integer power here, where according to basic algebra we would have no simple way of multiplying out to get a finite number of terms. And so it would be very hard to differentiate such functions without the chain rule. So let's look at a slightly more complicated example. Let's look at h of x is equal to, let's say, a slightly more interesting function inside x squared plus 5, for example. But let's have this to the power of 1/2. Now, identifying with the chain rule, you always want to identify the inner and the outer functions. So the inner function, g of x, is x squared plus 5. And the outer function, f of g, is simply g to the power of 1/2. I can now differentiate those. So I have that dg by dx is equal to 2x, and I have that df by dg is equal to 1/2 g to the minus 1/2. You see, I'm just using these basic ingredients of powers that we know how to differentiate very straightforwardly, and then the chain rule says we just multiply these two together to get the derivative. So therefore we would find that dh by dx is 2 times x multiplied by 1/2 g to the minus 1/2. The 2's cancel and I get x, and then g, remember, is x squared plus 5, and that's to the power of negative 1/2. And there is the derivative of that function according to the chain rule. And this is really marvelous, because there would be no way to do this differentiation using basic algebra. There is something, as I mentioned, called the binomial theorem, which is related to the Taylor expansion, where there would be a way of representing this by an infinite number of terms, differentiating them in turn, and then concatenating them again to get this function. But of course, if you can do this differentiation in 2 lines like we've done here, then that's the way to go. So the chain rule gives you a marvelous way to do these kinds of derivatives of composite functions. And let's just take stock here, because really, although I'm following kind of a recipe here of identifying an inner and an outer function, differentiating each and then multiplying them together, with enough practice you won't really even need to do that, because you'll see that what we're actually doing when we're doing the chain rule is we're saying an inner function. So we think of that as a block, and we just differentiate the thing that's acting on that inner function, which is a cubic here. So we bring the 3 down, have this thing squared, and then we differentiate the inner function. Here we would just get 2. So you can very quickly see we're just going to get 6 times this thing squared, which is indeed the answer. Here, for example, we have something inside multiplied to the power, raised to the power of 1/2. So we would differentiate this, we would bring the 1/2 down, we would have this thing to the negative 1/2, and then we would differentiate inside just to get 2x. That 2 cancels the 1/2, and we have then x that comes from differentiating this times this object to the negative 1/2. So I won't do that kind of very slick chain rule differentiation in this tutorial. I just wanted to point that out because after enough practice you'll find that you're able to do these actually very, very rapidly. Let's do a couple of examples using trigonometric functions. So let's imagine we have a relatively straightforward one. Let's say we have h of x equals, for example, sine of 4x plus pi over 3. Okay, notice I'm using radians here just as a natural unit of angle. Now the inner function is just 4x plus pi over 3. Whoops, 4x plus pi over 3, and the outer function is just the sine function. Differentiate those straight away. We have that dg by dx would just be given by 4, because obviously we differentiate constant, we get 0, and the derivative of the outer function with respect to the inner is just the derivative of sine g, which is cosine of g. And therefore, multiplying these together gives us our result. So dh by dx is 4 multiplied by the cosine of g, and g of x is just 4x plus pi over 3. Notice in the final step I switch from the symbol g, writing its explicit form in terms of g of x just in the last step. So 4 cosine g is sort of the answer, and then we recall that g of x is 4x plus pi over 3, and we write that explicitly, and that gives us then the derivative explicitly in terms of x. Right, let's do another trigonometric example. Let's imagine we're differentiating h of x equals, for example, 2 times the times sine squared x. Okay, so this one's kind of cutely different to the one we've just done, because now the inner function is actually sine x. So you do have to sometimes just pause for a moment to think, what are the inner and outer functions? The inner function here is actually sine x, and the outer function is squaring that and multiplying by 2. So the outer function is multiplying 2 and squaring the argument. And we can see if I plug g as sine x here, I get 2 sine squared x, which is what we have here. So we just differentiate. So dg by dx is cosine of x, and df by dg is 4g. Sounds like something to do with telephones. 4g. Sad that I should even think of that. There you go. And then we multiply these together to get our final result. So we have that dh by dx is cosine of x multiplied by 4g, and g is sine x. And so just to write that more neatly, it's 4 sine x cosine of x. Which actually, I mean, you could do something quite cute here. You could actually say, well, that's, I know from my trigonometry that that's actually equal to 2 sine of 2x. And then you could say, well, could I have gotten that from here? And actually, you might remember that when we think of cosine of 2x, we can write cosine of 2x as 1 minus 2 sine squared of x. So this actually in disguise is 1 minus cosine of 2 of x. So this is actually quite cute, because actually we could have, by writing h of x in this way and using the chain rule, where now the outer function is 1 minus no, well, actually we have two functions now. We have just a constant, then we have a composite function, which is cosine with an inner function of 2x. You could use the chain rule on this. This differentiates to 0. Negative cosine differentiates to sine, and differentiating the inner function we get 2, so we get 2 sine 2x. So this is actually an interesting example because we have a function where we can think of it in two different ways as two different composite functions, apply the chain rule differently in each case, but of course we come to the same answer at the end. Right, now finally, in this little bit of space I have left, I want to look at the exponential function. This is not on the Scottish Higher Exam syllabus, but we have looked at the exponential function a couple of tutorials ago, where we saw that the derivative of the exponential a to the x is a constant which depends on the base times a to the x, but we didn't have any means at that time to work out that constant. But we can do that here now in the following way. Let's think of having a function h of x equals e to a constant e raised to the power of a constant times x. So this is a very simple example now. The inner function is just bx, and the outer function f of g is just e to the g. So you'll see exponentials are a piece of cake to differentiate. The derivative dg by dx just gives us b, and the derivative df by dg, beautifully, and just you never get tired of looking at that, is just e to the g, because it's this very special function which is its own derivative. And so putting those two things together, dh by dx is the product of these two things, which is just b times e to the g, and g is bx, so it's b times e to the bx. And this is a very, very important outcome of the chain rule, which is that when you differentiate an exponential where you have a number in the argument of the exponential multiplying x, when you differentiate, that number just comes downstairs. A very, very important result, and I don't know why it's not on the higher syllabus, because you have all the tools to easily understand and utilize this, but it's good to see it here. This underlies so much, particularly in physics actually, when you look at exponentials in equations involving rate of change. Whether it's things like radioactive decay, or whether it's slightly more complicated equations that describe waves and oscillations, this fundamental result underpins the mathematics of those physical applications. So just at the risk of being tiresome here, if you have an exponential e to a constant times x, the derivative is simply that function multiplied by the constant upstairs. It just comes down. And this enables us to answer that question about what is the derivative of a to the x, because if I have a function a to the x, I can think of that as it's going to look strange, but I'm going to write this as e to the natural log of a to the x, because I'm allowed to do that, because e to the natural log is a function of an inverse function, so anything can be written as e to the log of that thing. And then using the law of logarithms, this x comes outside, and this is e to the x log a. And because I know how to differentiate e to the x times a constant, that constant comes downstairs, I then have the result that I wanted, which is that if I have a function a to the x, then its derivative, I can sort of get through the back door by using the chain rule. The derivative of that function is, I bring down a log a, and then I have e to the x log a, which is just a to the x. So I have the natural log of a multiplied by a to the x. And that answers our question. We knew that the derivative of a to the x was a constant that depended on the base times a to the x. We knew that that constant was unity when the base was equal to e, and what we've shown here using the chain rule is that actually that constant, that elusive constant, is just the natural logarithm of the base a. And of course, when a is equal to e, the natural logarithm of e is 1. So that's quite a nice way to end this tutorial here then, applying the chain rule. We've done lots of examples here. Just a quick recap. We looked at a very simple example first where we could do it by hand. We could calculate the derivative by hand by multiplying out, differentiating term by term, factorizing, getting an answer, and then using the chain rule we can get to that answer straight away. So for such functions the chain rule is a matter of convenience. But then we looked at lots of other examples where actually you simply have to use the chain rule to do the differentiation. We looked at a non-integer power of a polynomial expression. We looked at the sign of a function which was not just x. In this case it's a number multiplying x plus a constant, which you often see at the higher level, and how to differentiate that. We looked at a function of a sine function, so we had a square of a sine function. And finally, we just looked at the exponential to see this very important result that when you have e to a number times x and differentiate that, that number just comes downstairs. Very important result. And as I mentioned a few moments ago, one can just use that to answer that sort of perplexing question, what is the constant that you get when you differentiate a to the x? It is just the natural logarithm of a. Good. I hope you found that helpful. The chain rule is such a powerful result and just such a beautiful piece of mathematics. It's nice when you have beauty and utility combined in such a powerful way. Right, so we're going to move on to the next topic of stationary points, which is also very important, but I think less glamorous than this, but a very important topic in mathematics and science. So I look forward to seeing you then. Thank you.